Well, it's great to be here. Here's the idea. 13.7 billion years ago, the universe was hot and dense. We know it's hot because we see the radiation. Bob Wilson saw it, heard it with his radio telescope. And we also see that the universe is expanding, that the galaxies are moving out, moving apart from one another. And what I'm here to talk about tonight is very briefly to tell you that the expansion of the universe, which we've known about now since about 1930, is speeding up. And the thing that's making that happen is something very much like that mysterious anti-gravity stuff that Alan Guth was talking about. There's some property of space itself operating now much, much later in a much less energetic way, but nevertheless, some quality of space so that as the universe expands, the density of that stuff stays the same. It sounds familiar. And that could be the origin of the cosmic acceleration that we see. So that's the story I want to tell you. I better get going because it has a lot of moving parts. So I show you here a galaxy. This is a big system of about 100 billion stars, more or less like our own. But in this picture, if you look down in the lower left, you'll see that there's one star, which is, for a little while, glowing as brightly as many billions. And that's a supernova explosion in which the star has a thermonuclear explosion. It explodes like a bomb. Do not worry, the sun will not do this. And they are extremely bright, and we can use those to try to judge the distances to galaxies. The story really starts in 1917, more or less. At that point, Einstein was working away on his theory for general relativity, and astronomers were working on studying the universe. At that time, what astronomers meant by the universe was the Milky Way galaxy. They thought that that might be more or less it. But the most important thing in this picture is that little item over there, which is another galaxy. That's the Andromeda galaxy M31, which is equivalent in size to the Milky Way, but just very much farther away. And as I'll show you, it's galaxies all the way out. So here's Einstein in a picture taken more or less in this period. This is a photograph taken on photographic emulsion, not like the electronic detectors that you have in cameras or phones today. And you can see that during the time the shutter was open, a guy left that seat. The other person back there disagrees with Einstein and is shaking his head. But the new thing that is really so impressive is that we're now scanning the plates the way we are scanning the Harvard plate collection so we can see what people were thinking. And Einstein was thinking that the universe must be static, that is, not expanding or contracting. And he said so, and he put a piece of mathematics into his equations to make that work. What he did was he put in a cosmological term, what we call the cosmological constant, and he said, this is in German, if you're in the back, I'm translating it. It says, that term is necessary only for the purpose of making possible a quasi-static distribution of matter as required by the fact of the small velocities of the stars. So people often say Einstein had a philosophical idea. Well, he may have had a philosophical idea about an eternal universe, but what he said was the reason is that he was talking about the actual measurements of stars in the Milky Way. And the velocities of the Milky Way stars are, in fact, small. But that was looking in the wrong place because it isn't the properties of the Milky Way, it's the properties of those other galaxies, like the one I showed you a second ago with the yellow circle around it, are the ones that really matter. And the story of discovering that there was a big universe really began right in this building. Here's Henrietta Leavitt, who worked here at the Harvard College Observatory, and she worked on variable stars, stars that get bright and dim, and she noticed something very interesting about a particular kind of variable star. She said, it is worthy of notice that the brighter variables have the longer periods. The period is the time it takes to get bright and dim. It corresponds to the vibration, the physical change in size of the stars. So there's something that doesn't depend on the distance, that's the period of vibration, that can help you with the problem of finding distances, because if you're looking out into the night, you see stars, but some are bright, some are dim. You don't know which ones are nearby and which ones are far away. But if you can measure something, like the period, and find out how bright the star is, then you can properly assign it the distance that it ought to have. So people thought that was quite interesting. And one of the applications of that was to look at the Andromeda Galaxy. So here is a picture taken in 1923. It's a photographic plate. It's a negative. And what you can see here is the fuzzy ball. That's the same thing that I showed, like the galaxy I showed a minute ago. And then there's some markings on here. Up at the top, these things that are N. Hubble was looking for novae, so he marked them with N, where he thought they were new stars. But up at the top, there was something that was a nova, but then he said, gee, I see that one again. It was something was in fact a variable, and in fact, one of the same kinds of variables that Henrietta Leavitt had been studying at the Harvard College Observatory. He could measure its period and figure out how far away this thing was. This system is not part of the Milky Way. It's 2 million light years away. It takes light 2 million years to get here. And that was sort of the beginning of understanding that we live in a big universe. The other piece of it is, of course, we live in an expanding universe, a universe with motion. And here's Vesto Melvin Slifer at the Lowell Observatory with a spectrograph measuring the light from galaxies. Then from the light from galaxies, you can tell whether it's coming toward you or going away from you. What Slifer found is that with his little telescope and his little spectrograph, he could measure the velocities of a couple handsful of galaxies, and almost all of them are moving away from us. Well, Hubble put that information together, the velocity going up this way, distance going out that way, and what you can see is there's a good relation between those two. Well, actually, not so good a relation between those two. The data was pretty crummy at the beginning. It's always crummy at the beginning. It gets better over time. And here's what you see, and I'll show you some really crummy data. No, we had some crummy data too. But here's what you see. Over there is 0. And as you go farther away, this is the distance down here, the galaxies are moving away from us more rapidly. It's like something that's just stretching out in all directions. If by the power of the director of the Harvard-Smithsonian Center for Astrophysics, I could make this auditorium twice as big in the next second, what would you see? You'd see your neighbor, who's 1 seat away, would be 2 seats away. But somebody who's 4 seats away would end up 8, and somebody who's 8 would end up 16. The nearby people would seem to be moving away from you, if you can imagine this. The distant ones moving away from you more rapidly. But it's not because they know anything about you, okay? In fact, everybody would have the same view. So you'll notice that there's 0 here. This is the 0 line. And there are a few galaxies that are approaching us. It turns out that the Andromeda Galaxy, shown here, is approaching us. And this, have you checked your homeowner's insurance? Okay, so I know that most of the members of the Harvard faculty believe that this is the correct interpretation of the Hubble diagram. And I've discovered by teaching undergraduate classes that that view is shared by most of the undergraduates as well. That they believe that this shows what they've always known, that they are the center of things. However, as I just tried to indicate, it doesn't matter which of you takes the point of view of seeing the things moving away from you. If the space is stretching out in all directions, then everybody will see a universe that obeys Hubble's law. Okay, so the universe that we see is this complicated thing in which there are galaxies in the foreground and galaxies in the background. It's hard for us to sort out the distances. Some of them we can do, and if we can extend Hubble's law out to bigger distances. Bigger distances correspond to longer times. The light travels at the speed of light. That's a foot, which is a unit used in the United States and in Myanmar. In a nanosecond, a billionth of a second. So I see the people in the front row as they were a few billionths of a second ago, and the people in the back look younger because the light left them some time ago. Same thing you said, Alan. And so it must be true. So when we look out into the universe, we see 4 galaxies in the foreground, galaxies in the background, and it's our job to figure out what their distances are and to measure their velocities. If we do that, by looking at the distant ones, we can see what the universe was doing back then, when it was young. Well, Einstein gave up on that cosmological constant in the 1930s. And so if you go to the National Academy in Washington, there's a very nice statue of Einstein. Shows him, historical details are correct, no socks. And it shows on this tablet, which he brought down from a mountain, a number of equations. There's the fundamental equation for general relativity, no lambda in it. Here's the photoelectric effect. They gave him the Nobel Prize for that, but he didn't bother to pick it up. And here's E equals mc squared. They were afraid to give him the Nobel Prize for that. Anyway, there's no lambda. Einstein more or less gave up on this cosmological constant because he had invented it to make a static universe. It's an anti-gravity sort of thing. If the universe was expanding, he said, well, never satisfactory anyway. Okay, so you can write down equations as Mr. Friedman did and Mr. Lemaitre did, and you can calculate what the history of the universe might be with different constituents in it. If it has gravitating stuff, that'll slow it down. If it has some of this cosmological constant, that could make things speed up. And so here's the idea. This is time down on this axis and size. Think of it as the separation between two galaxies over there. And when the universe is expanding, its size is getting bigger. That's going up on this diagram. If it's slowing down, that's a deceleration. It will be curved kind of downward. If it's accelerating, it'll be curved upward. So you already know the answer, so I'm not going to try to keep you in suspense. The answer, which was quite astonishing, is that we live in a universe which actually follows something like that red line, at least for now, and has, over the last 5 billion years or so, been accelerating. How do we know that? Georges Lemaitre is one of the guys who worked out the equations that show you how a cosmological constant would affect the expansion. And he's also one of the people who realized if there's expansion now, then the universe might have been smaller in the past. You could go back to some time, he thought, when there might have been kind of a primeval atom, which is really something we recognize as the Big Bang. And then he said in this kind of poetic way, the evolution of the world, and he means the whole universe, of the world can be compared to a display of fireworks that has just ended. Some few red wisps, ashes, and smoke. Standing on a well-chilled cinder, we see the slow fading of the suns, and we try to recall the vanished brilliance of the origins of worlds. Good. Good, George. This is just prose. Here we go. So how do we do this? How do we find out whether this expansion from this vanished past follows acceleration or not? You look deep into the universe. Here's the telescope in Chile that we used to do it. And now this photograph is taken without a flash or anything, with an electronic detector. And you know that you can do that now because the electronic detectors are 100 times more efficient than the photographic plates that Hubble was using. And we have something that's brighter than Henrietta Leavitt's stars to look at. We use supernovae, these exploding stars that burst out with about 4 billion times the light of the sun. They're about 1 million times brighter than the stars that Henrietta Leavitt was using. The problem is they're rare. You know, they're about 100 years apart. It's about one in a century. So even people like me or Owen, we have not seen a supernova in our own galaxy. It's been since 1604 since somebody has seen one in ours. So how do you get around that problem? You can't assign a graduate student the problem of staring at a galaxy for 100 years. They will not do it. And the answer is, of course, you have to look at a lot of galaxies. And the digital detectors that we have and the computers that we have allow us to do that. So here's an image. You can see lots of galaxies. Those are these little fuzzy things. But the galaxies that are really interesting are the ones that are very far, the ones that look just little like grains of sand in this picture. They look like little dots, but they are 100 billion stars at distances of billions of light years. Okay. And here's how you find the supernovae. You write software because it's too boring to look at these pictures. And you take a picture and compare it to a picture taken a month ago and subtract them in a computer. So things that stay the same, like this nice spiral galaxy, subtract away. And things that change are shown in the difference, and usually with a red circle around them. So that's a candidate for a supernova. You can take its spectrum the way Slipher did, And you can measure its brightness the way Hubble did, and you can put it on the Hubble diagram. And we've done that. So here is the Hubble diagram. Now this is a nice set of data, modern data, where, let's see, what is this? This is the velocity and that's the distance, but never mind. And you can see the data. And this curve that's going through it is for different cosmologies, different universes that have different amounts of this dark energy, the cosmological constant, or anyway, the springy stuff that makes the universe accelerate. And you can do this problem. Arturo, are you paying attention? You can do this problem. You watch this, and you see, ooh, that's good. Ooh, that's too much. It makes the Hubble diagram curve a little bit, and you can see it's as this ticks through about 0.7 that you get the best fit to the data. What that means is 3/4 of the universe is in the form of this weird dark energy, this strange stuff that we just discovered in 1998. So it looks easy now, but it was Galileo who said, all truths are easy to understand once they are discovered. The point is to discover them. So here's Einstein. Of course, he'd been dead for many decades, but in 1998, looking quite surprised, but he's carrying a sheaf of paper that has a lambda on it. He said, I thought of that. I could have been a good scientist, well known. Only I had stuck to my guns. Okay. And awards have been given for this. I, for example, received the XLR8N Universe license plate from the state of Maine. My students had to settle for a somewhat more Baroque prize awarded in some Scandinavian country. Saul Perlmutter, who was an undergraduate at Harvard, Brian Schmidt and Adam Rees, who were my graduate students, won the Nobel Prize in 2011 for the discovery of the accelerating expansion of the universe through observations of distant supernovae. Now they're shaking hands with some Swedish guy. And this information can be combined with other information. So here is a kind of picture, a baby picture of the universe, a picture of the glow from the Big Bang of the microwave background made into a picture. Most of the signals subtracted off, and what you're just seeing are the variations from place to place, the freckles sort of on the baby picture of the Big Bang. And just as I showed you that I got a somewhat inferior prize for my license plate and so on, I show you my own baby picture, which you can see over here won the Honorable Mention Award for the 16th Children's National Photograph Contest in 1950. Just saying. Honorable mention. Again. Okay. Okay. So if you combine information from the microwave background, how galaxies are clustered, and other information, you can sort out how much of the universe is in each component. What you find is that atoms, the stuff that we're made of, is about 4%. I don't know how that makes you feel. It makes me feel very special. There's other gravitating stuff that we call the cold dark matter. We're pretty sure that that is there and making the orbits in galaxies, but it's not the ordinary stuff that we're made of. And as you saw, as that line was ticking through the data points, about 3/4 of this diagram is labeled dark energy. Now, just because we can label it doesn't mean we know what it is. But it could be the cosmological constant or something very similar to it, and it could be very similar in its properties, is very similar in its properties to the whatever that thing was that Alan Guth was talking about that makes the inflation take place in the first zillionth of a second. So it's something that is a mystery in science, and this is the best thing. If we have mysteries, if we have the unknown, we have something to do next year. Personally, I'm fond of the atoms, and my part of the pie is the tastiest part of the pie. At the Ig Nobel Prizes, I ate that, but anyway. So when you go onto the blogosphere, people say, oh, those scientists, they don't know what's really making this happen. The dark energy, dark matter, they're not too sure about it. But you know, we're used to judging the presence of things by the effects they produce. And what we see is this effect, the acceleration of the universe, the change in the expansion over time. If you look out the window on a windy day, you see the trees moving. And you know, if somebody asks you, well, what's happening? You say, well, it's the wind. You do not see the wind. You see the effects of the wind. And in the same way, we don't really see the dark energy, but we see the effects of it, and we can learn something about its properties by doing that. Finally, I'd just like to say this investigation is like a lot of things where we try to understand what the world is made of and how it works. And this is done by scientists in the way I've alluded to here, if not exactly shown. And it's also done by artists. You know, if you go to the Museum of Fine Arts, there's the masterpiece by Paul Gauguin. And, you know, he's asking the same kind of questions that we try to answer scientifically. Where do we come from? Where are we? Where are we going? Thank you.